their PDFs. Okay. Now just you have to see a very good afternoon. Please stay on the line. Hello. Hello, students, can you visible here?
Yes, sir.
Okay, very good. Today, already some PDFs just you have to see or not, seeing or not there through WhatsApp. I have posted. There is in the examination point of view, some PDFs are also dispatched. The last two classes are also with the brief explanation and the definition of a vector space. Just you have to see here and definition of a vector space and what is the real vector space and what is the complex vector space. Now, in the field of the real numbers, V of R is called real vector space. In the field of the complex numbers, this is called the V of C is called the complex vector space. And what is the null space or zero space and some elementary properties of vector spaces. Now, these are also well explained in the previous session. Okay. Now, in the same manner, the brief examples of vector spaces, n tuples of the field elements is also to form a vector space with respect to vector addition and scalar multiplication. Okay. Now, and just we have to see here and another one. There are so many examples. The real value continuous functions defined on interval 0 and 1. Now that is also form a vector space and the m by n, the set of all m by n matrices to form a vector space to the addition of matrices and the scalar multiplication of matrices. Okay, this is the third example. And the next example are some ordered pairs, set of all ordered pairs to form a vector space. Okay. Now, this is the one. Now, this is one of the example, last example, see here. Now, this example, set of all ordered pairs does not form a vector space. Why? Because V of R is not a vector space. Now, this is the one of the example that is the belongs to which is not a vector space. Okay. Now, what is the vector subspace definition? Now, vector subspace definition is here. Just see and refer. To stay on the line. Okay. Now, this is one of the important definition of a vector subspace. Already last class we have to discuss it here. What is the vector subspace definition? Now, here capital W be any non-empty subset of a vector space, that is W contained or equal to V. Hello, students? Can you listen? Is there? Hello?
Yes, sir.
Okay, very good. Now, this is the vector subspace definition. And here W be any non-empty subset of a vector space is consisting. Now, those vector space, all the postulates must satisfy given the non-empty subset of a vector space, that is called a vector subspace. Now, that is W. In the same manner, V and addition is an abelian group, and W and addition is an abelian group. And scalar multiplication holds good, and here that is also W scalar multiplication holds good. Now, some distributive laws are also satisfied. Now, their distributes any two is are also satisfied. In the same manner, W is also the same distributive, all the possible distributive properties satisfied, at least two is there. Okay. So there are improper subspaces. What are the trivial subspaces? Or here what are the trivial subspaces? Now this is one of the important examples. The last session is also explained here. Set of 0 bar, 0 vector and capital V. There are trivial subspaces of vector space. Now, see this theorem already last class explained here. This is the necessary and sufficient condition of vector subspace. Students, listen carefully. Please stay on the line. Already last class this theorem is also very that is also explained here. What is that? here the vector subspace the necessary and sufficient conditions. Let V of F be a vector space and let W contained are equal to V. Suppose you have to see here. Already let V of F be any vector space. Now that vector space and let W is contained are equal to capital V. The necessary and sufficient conditions for W to be a subspace of V. Suppose here V be any vector space. That non-empty subset is said to be a vector subspace and has the following two conditions. Now what are that? Here alpha and beta, those elements are consisting given the subset. Now, and in the same manner, the closure condition alpha minus beta is also belongs to W. Minus can also be listed as alpha plus or minus is there. Okay. Now plus or minus alpha plus or minus beta means addition is closed with respect to two elements under the operation is subtraction. Subtraction can also be listed as plus or minus is there. Either of plus of minus. Okay. Now plus of minus is minus, so that's why alpha minus beta belongs to W is there. In the same manner, here A being the field element and alpha being the subspace element. Here A alpha means scalar multiplication must holds in the subspace. Okay, that's enough. This is one of the important and necessary and sufficient condition of a subspace. Now already this theorem is also well explained in the last class is there. First of all, so we have to take it W is a vector subspace of P. Once again, I have to repeat because that subspace is necessary and sufficient conditions very most important in the final examination. Now here there are according to the two conditions we must derive the subspace theorem. Okay. Now that is alpha minus beta belongs to W and A alpha belongs to W. Now those conditions are applying the subspace proved part. Okay. First of all, so what is the necessary part? W is a vector subspace of V. Here V is the vector space and then their subspace is W. Now, according to that, by the definition of vector space, in the same manner, W under H is also is an abelian group. And before the abelian group, we must prove that a group part is there. And before that, that V under H is an abelian group is there. That according to that group, now then the subset is a subgroup is there. So suppose W is a subgroup of E under H, and in the same manner W under H is also a form a group is there. And according to this condition, alpha belongs to W, beta belongs to W, alpha minus beta belongs to W. That is alpha plus of minus beta belongs to W, alpha minus beta belongs to W. Closure condition is verified in the group status. Now W is a subspace of P. Now here W is closed under scalar multiplication. What is the scalar multiplication under vector space for A alpha belongs to P? Because W contained are equal to B. Therefore, W is a subgroup of P. Therefore, in the same manner, here the same scalar multiplication, A belongs to field element and alpha belongs to W. A alpha belongs to W is there. Next one, sufficient condition. Now, sufficient condition means first of all, here V be any one of the vector space, and according to the vector space, just you have to assume the one of the non-empty subset is there. W not equal to pi is containing of P means W be a non-empty subset of P satisfying the two conditions. Under the conditions alpha minus beta and A alpha belongs to W is there. Now, sufficient condition that non-empty subset to first of all is to form a group, and second one abelian group and scalar multiplication and with respect to those conditions. Now here A alpha belongs to W and alpha belongs to W because one vector is consisting to be same one vector is consisting given the non-empty subset, and second vector is also because those conditions depends upon the additive identity. What is the additive identity? 0 bar is the additive identity given in the vector space part. Therefore, that's why non-empty subset is also consisting same non-zero vector is there. That is the additive, the 0 vector is there. Therefore, which is the when we get the with respect to the offer, with respect to the condition, how to get the 0 vector? The second element is also we have to take, and that element is also equivalent to alpha is also in the same manner. That is alpha minus alpha. Now, condition is also applied here. Now, the replacing of beta by alpha is there. Alpha minus alpha Now we are getting the additive identity is there. Okay, so vector is also zero vector additive identity. The same zero vector is also consisting of W. Now, what is the additive inverse? Additive inverse is alpha being one of the vector is there given the non-empty subset. Yeah, additive inverse is inverse of the element is minus alpha. Now, how to get the minus alpha? First vector is zero vector because identity is completely depends upon the inverse. Inverse is completely depends upon the identity. Therefore, zero vector belongs to W and alpha belongs to W. Now that those elements of is applying the first condition and replacing of 0 minus alpha, we are getting the minus alpha is there. Okay, so alpha being the alpha is the inverse is minus alpha. Additive inverse of each element of W is also in the W. Okay, that's it. In the same manner, alpha and minus beta belongs to W. This is minus beta. Sweets. Alpha belongs to W, beta belongs to W, and beta is also now then the inverse of the element is minus beta. So alpha and minus beta, those elements is substituting the first condition. Alpha minus of minus beta, we are getting alpha plus beta. Therefore, that's why this is the closure condition is also verified under addition vector and addition part. So given the non-empty subset, closure condition is verified. In the same manner, all the postulates must satisfy given in the non-empty subset. Associativity, already identity is there, additive identity is there, additive inverse is there, scalar multiplication is there. Now, remaining postulates, commutative property is also in the same manner, associativity is also satisfied, and the same manner, commutative is also satisfied. Therefore, that's why W and reduction is an dependent group. The second condition, scalar multiplication holds in the same manner given the vector space definition. Given in the non-empty subset is also satisfied. Scalar multiplication is satisfied. That is W is closed under scalar multiplication under the postulates. Okay, that is hence why as that W is contained are equal to V. Therefore, V under addition and scalar multiplication is a vector space, and given the non-empty subset when all the postulates were satisfied given the under the vector space definition. Now we have to derive here W itself is a vector space and the operations of is there. That's why W of F is a vector space through the two conditions. That is the two-step test. Only one-step test is A alpha plus B beta belongs to W. This is the other theorem. But because these proofs are not included in your textbook is there. That's why I must mention in this session, especially those proofs are available in this class. Okay. Now these are necessary and sufficient condition of the non-empty subset of a vector space. Let V of F be a vector space. Now that non-empty subset is contained or equal to vector space. Now according to the necessary and sufficient condition of W to be a subspace. When it is the non-empty subset to be a subspace of P. Now direct condition is A alpha plus B beta belongs to W. Now their proofs is also already last class is also derived. First of all, so necessary part direct condition W of F is a subspace, and when the subspace before that it is a vector space. Before that it is a vector space is there, and A belongs to F and alpha belongs to W, and the scalar multiplication is A alpha belongs to W, and B belongs to F and beta belongs to W. B beta belongs to W. There are two scalar multiplication given in the subspace. Now those scalar multiplications under the vector addition, A alpha plus B beta belongs to W is there. Next one, let W be any subject part is there. Let W be any non-empty subset of vector space satisfying the given condition. What is that? Here. Now, first of all, so given the non-empty subset is W is there. That non-empty subset of the elements here A comma B being the field elements and alpha beta belongs to W. A alpha plus B beta belongs to W. That is the direct condition is there. Now before that A equal to 1 and B equal to minus 1. We are getting alpha minus beta belongs to W. And in the above theorem is mentioned here. Okay, alpha minus beta. Okay, and the scalar multiplication is and the identity part is alpha belongs to W means alpha belongs to B. And identity part, identity element is 1 is there. 1 into alpha equal to alpha. Now both are now this is comparing it with the alpha scalar multiplication. And for that, H contained are equal to G. A and B be any two elements given the subgroup. A B inverse belongs to H. And G under circle is a group and H under circle is a subgroup of the part. Therefore, W under addition is a subgroup of the abelian group. The same manner, W under addition is an abelian group. Again, taking B equal to 0 in the A alpha plus B beta. So, A alpha plus B beta means B equal to 0. We are getting the scalar multiplication. Therefore, W is closed under scalar multiplication. Alpha minus beta belongs to W. When these two conditions already we have discussed in the first theorem of subspace. That's why here the non-empty subset, all the postulates must holds in the W of F is in B. Therefore, W of F is a vector subspace. Okay. Now that's enough. This is the direct condition, and this is the B equal to 1 is there. Now the condition is also satisfies the subspace. A alpha plus beta belongs to W. This is also necessary and sufficient condition of a subspace of a vector space. Now, even the non-empty subset is a vector space. Students, listen carefully. Here, A alpha plus beta belongs to W. This is also one of the important subspace of necessary and sufficient condition. Already we have discussed this one. Those examples are also satisfying the subspace part. Okay. Now triad point is there. X, Y, 0. This is the triad point. This triad point is a subspace. Suppose here x1, y1, 0 is there. The element is alpha. And x2, y2. There are distinct elements are given the triad point. Distinct means x1 and x2, y1 and y2. Okay. There are different distinct elements given in the ordered triads for this set is W. So we are taking alpha and beta elements. Alpha is one of the vector and beta is another vector. That triad point through this condition, triad point is x1, y1, 0, x2, y2, 0. Now those elements are the field elements. Now here suppose here the field elements is A and B are any two field elements. So which is the suitable example of subspace? Is the suitable example. Or the triad point is a subspace. Suppose A and B are any two elements given the field. That is A alpha plus B. A of alpha is x1, y1, 0 plus B of beta is x2, y2, 0. Now we must prove that we will show that subspace part. Triad point is a subspace part. Subspace means that is the direct condition is A alpha plus B beta. That is AX1, AY1, A0 is 0, BX2, BY2 and 0. Therefore, this is AX1 plus BX2 and AY1 plus BY2 and 0 is there. So this is x coordinate, this is the y coordinate and this is 0. Therefore, this is also triad part is there because z coordinate is 0. That's why it is the subspace condition is verified here. Therefore, A alpha plus B beta is also consisting same triad point. So that's why this is the triad or the triad point is a subspace. This is one of the finest example of subspace. Just you have to see and refer. This is the second example. Here the condition is Px plus Qy plus Rz equal to 0. This is one of the condition. Set of all triads x1, y1, z1 of elements given in the field. According to this condition, this is also a vector subspace. Now we are taking, there are different elements x1, y1, z1 and x2, y2, z2. Those triads is applying given in the condition ax1 plus bx1 plus by1 plus rz1 equal to 0, bx2 plus 2y2 plus rz2 equal to 0. There are two conditions. Right? Because now here A and B field elements the subspace condition is A alpha plus B beta. We are replacing here A of alpha is x1, y1, z1, beta is x2, y2, z2. We are getting the element is ax1 plus bx2 and ax2 plus ay1 plus by2 and az1 plus bz2. Okay, this is okay, and this is the one of the part. The same manner P of Px means ax1. This is x. This is y. This is z. Is point at this point is also belongs to the given under the condition P of ax1 plus ax2. This is Q of ay1 plus by2 plus Qr of this is Q. What is that? Third coordinate az1 plus bz2. Now we are getting the point is this condition is 0 and this condition is 0. By the first and second equation, we are getting now that is the verified part. So therefore, A alpha plus B beta is also satisfies the subspace condition Therefore, that's why here, according to this condition, Px plus Qy plus Rz equal to 0 through the triad point x1, y1, z1, x2, y2, z2, and basically x, y, z being the elements of the field. Therefore, that's why this condition is verified to form a vector space. Okay, that's it. That's it. Now, there are so many examples are also mentioned here. Okay. Now, just you have to see and refer algebra of subspaces. Okay. Already last class, this definition is also very this is one of the important part. Algebra of subspaces means algebraic symbols, union and intersection. What are the properties of under the union and intersection of the subspaces? Hello. Is that followed? Students. Anybody is there? Any doubt? No? Is it okay? Can you hear me? Hello? Please respond. Hello? Is it okay? Okay, just you have to see here. Algebra of subspaces. What is the algebra of subspaces? The intersection of any two subspaces W1 and W2. Okay. The any two subspaces is there. The intersection of any two subspaces is a subspace. So therefore, W1 and W2 be any two subspaces. What is the here? Is it okay? Any doubt? Okay. The intersection of any two subspaces is a subspace. So W1 and W2 be any two subspaces, then their intersection W1 intersection W2 is also a subspace. Now this is very simple proof is there. Okay. First of all, P of F be any vector space, and those subspaces denoted by W. Now directly, now all the postulates non-empty subset must satisfying the conditions of a vector space. That's why those that non-empty subset is a vector subspace. Here, first of all, zero vector is consisting W1 and zero vector is also consisting W2. Therefore, W1 and W2 it is consisting of the element is zero vector is there. Therefore, common element is 0 bar is consisting W1 intersection W2. That's it. Here, A and B, because at least zero element is there. That's why the intersection of the subspace is not non-empty part. Okay, at least one element is there, so that's why it is non-empty. So A and B be any two field elements, alpha and beta be any two elements given in the intersection of the subspaces. Therefore, that's why alpha comma beta belongs to W1, and alpha comma beta belongs to W2 is there. Therefore, A, B and the field elements and alpha comma beta belongs to W1. That's why A alpha plus B beta belongs to W1. And A comma B belongs here, and alpha comma beta belongs to W2. A alpha plus B beta belongs to W2. Therefore, A alpha plus B beta belongs to W1 intersection W2. Okay. Now that is the direct condition of the subspace must be satisfied under the intersection of the subspace. Therefore, a W1 intersection W2 is a subspace of F. Now that is a very simple proof. Now common element, field elements are common, but here R alpha and beta belongs both elements are consisting W1 and W2 is there. Now, according to the W1 elements, just you have to write the subspace condition, and according to the W2 elements, to write the subspace condition. Now, the same element is also repeated in the W1 and the W2. That's right. A alpha plus B beta is the necessary and sufficient condition. One-step test, only one-step test of in the subspace. That's why there is the common element in W1 and the W2. So that's why intersection of the subspace is W1 intersection W2 is a subspace. Now, already this proof is also seen in your textbook is there. Okay, but it is not here. The above theorem intersection of the subspace is a subspace. Okay. Now, for your purpose, now in your presence, just you have to mention here. Okay. The intersection of any family of subspaces of a vector space is also a subspace. Okay. Now, first of all, what is the intersection of the family? Now, intersection of Wi equals to W, and the same manner at least zero element, zero vector is there. So that's why a family of intersection is non-empty is there. You write the alpha and beta elements in the intersection of the subspace. Therefore, number of subspaces of the path is denoted by arbitrary family. So that's why alpha and beta belongs. Simply, it is notated as Wn is there. Therefore, A and B field elements, A alpha plus B beta belongs to Wn, that is intersection of Wi. Here, I equals to 1 to n. Therefore, same condition, subspace condition under the arbitrary intersection of the family. Therefore, intersection of the subspace is also a subspace. That's enough. Now, union of the subspace is not a subspace. Give example. This is the practice test in your textbook. Okay. Practice test in your textbook. Now that's the solution is they give example of union of the subspaces. It may not be a subspace. So first of all, you have to take in the W1 object point is 0 by 0. Here y coordinate is y being the real number. And W is also z coordinate of the right point is 0 0 z. Here z being the real number. There are two non-empty subspaces. The non-empty subsets, that is the subspace part. So W1 union W2 equals to, okay, W1 union W2 equals to, union means that is the sum of the path here 0 of y plus 0 y, 0 union z equals z means z is there. Therefore 0 y 0 plus 0 0 z equals to 0 y z. But 0 y z is it consisting of W1 union W2? It is not consisting. Therefore, this element, this squared point is not consisting the given in this part, either W1 or W2. That's why W1 union W2 is not closed under vector addition. Therefore, union of the subspace is not a subspace. Now, in the same manner, the union of any two subspaces, when it is a subspace, and only one is contained in the above session is the union of the subspaces may not be a subspace. That is one of the example is there. But here, if it is possible, that is the theorem is the union of any two subspaces is a subspace. If and only one is contained in the other. Suppose W1 and W2 be any two subspaces of vector space. Now, when necessary part is so W1 when it is contained are equal to W2 or W2 is when it is contained are equal to W1. So, but it is when it is between the union of their part, W1 union W2, either W2 or W1 is there. Because before that W1 is a subspace, W2 is a subspace. Therefore, union of the subspace and comparing it with the W1 or W2, automatically W1 union W2 is a subspace of T of F. Okay. Now, sufficient part is there. Union of the subspace be a subspace. W1 union W2 be a subspace. Let us suppose that W1 is not properly W2. W2 is not properly W1. W1 is not properly W2 means there is here at least one element is consisting W1 and that element according to this condition that vector is not consisting W2 because according to the condition is W1 not contained as equal to W2. Suppose x belongs to W1, but x is not in W2. And in the same manner, W2 not properly contained in W1, there is y belongs to W2, but y is not in the W1. There are two contained equations. So therefore, x belongs to, now according to this one, it can also be written as x belongs to W1 union W2 and y belongs to W1 union W2. So, under the vector addition, x plus y, because the union of the subspace is the subspace. Therefore, according to that x plus y, it also belongs to W1 union W2. But here x belongs to y, and according to the condition, either W1 or W2 is there. Suppose, first of all, x plus y belongs to W1, and the first condition x belongs to W1, because already W1 is a subspace. Now, adding with x plus y. Okay. Now, those according to subspace condition, 1 of x plus y, we are taking the another two elements, one a alpha plus b beta. A value 1, b value minus 1 is there. So, x plus y plus minus 1 into x, because remaining element is y is there. According to that simplification, minus minus 1 into x belongs to W1. So therefore, after the simplification, we are getting the y belongs to W1. But from the first condition, from the second condition, y is not in the W1. But here y is in the W1. This is the contradiction of the part. And in the same manner, x plus y and the y belongs W2 because W2 is a subspace. What is the subspace condition? A alpha plus B beta. Here this is alpha and this is beta is there. So again, A and B values, so we are taking 1 and minus 1 is there. 1 into x plus y and minus 1 into y. After the simplification, x belongs to W2. But the first condition, x is not in W2, but here x belongs to W2. Therefore, this is also a contradiction. And now, those 3 and 4 both are contradicts first and second equation. In the same manner, W1 either contained are equal to W2, W2 are contained are equal to W1 is there. Okay, students, this is one of the important theorems of subspaces. Now, that is the algebra of subspaces. Now, last class is also well-established theorems here also explained here, and once again you have to repeat it here because subspace part is also completely depends upon the entire linear algebraic part. Okay, please stay on the line. Next one, linear sum of subspaces. What is the linear sum? Here, very important concept. Students, listen carefully. This is only subject purpose. Already, I have dispatched some other material in the WhatsApp group is there. Okay, and available numbers is also provided here under mine. Now, all PDFs, last 2 classes PDFs and this class PDF are also posted in the WhatsApp group. And again, some important problems and theorems. Overall, the part is also dispatched in WhatsApp group just to see and refer here. Okay, that is the 73 pages. Okay, don't forget this one. Linear sum of subspaces. Suppose here W1 and W2 be any two subspaces of the vector space. Here B of F be any one of the vector space. Student, listen carefully. Here B of F be any one of the vector space. Those subspaces is W1 plus W2. Sum of the subspaces is denoted by W1 plus W2. That is the linear sum. We read as a linear sum. Linear sum is of the set is W1 plus W2 equal to set of. We are taking the element is alpha 1 belongs to W1 and alpha 2 belongs to W2. That's why here the set of the element is alpha 1 plus alpha 2 such that alpha 1 is consisting belongs to W1 and alpha 2 is consisting belongs to W2 is there. That's it. Therefore, alpha 1 plus alpha 2 is there. Sum of the linear sum of the element is alpha 1 plus alpha 2. Now, according to the linear sum definition, corresponding to the subspaces, just you have to see and refer this theorem. This theorem is also very important in further session is also there. Okay. Particularly, just you have to observe given the statement. W1 and W2 are any two subspaces of a vector space. Okay, that's enough. Sum of the subspaces is a subspace because linear sum is a subspace of V of F. First one. Second one, this is the linear sum. It as linear sum. It is also a subspaces of V of F. And W1 contained are equal to sum of the subspaces. W2 contained are equal to sum of the subspaces. W1 union W2 contained are equal to sum of the subspaces. See and refer give the proof. Alpha and beta, there are two elements in the linear sum part. Alpha means to write as the linear sum, alpha 1 plus alpha 2, comparing it with the linear sum of the part. Beta is also one of the vector. Now that vector is also just you have to write the linear sum of this part, beta 1 plus beta 2. Therefore, just you have to observe this one. According to the linear sum elements, alpha 1 and beta 1, both the two elements are consisting in the W1 first subspace of a vector space. In the same manner, alpha 2 beta 2 is also belongs to W2. Therefore, A alpha plus B beta, because scalar multiplication of the first elements, A alpha 1, B beta 1 belongs to W1, A alpha 2, B beta 2 belongs to W2. That's why A alpha plus both the elements are consisting Now those elements is substituting in the subspace condition A alpha plus B beta. That is A of alpha means A alpha 1 plus A alpha 1 plus A alpha B alpha 1 and A alpha 2 plus B beta 2. Those elements are substituting here. We are getting this one A of A alpha 1 plus B beta 1 plus A alpha 2 plus B beta 2 belongs. This element is W1 plus W2. Finally, we are getting the condition is also verified under the linear sum of the part. So what is the condition? Subspace condition must be verified through the linear sum of this part. Therefore, that's why linear sum is a subspace. Now, just you have to remember the point is what is the vector subspace direct condition necessary in such a department? That is A alpha plus B beta. That is the one step or one step test or one step condition of vector subspace. Okay, you understand here? Okay, next one. Here, A1 belongs W1 is the first vector, alpha 1 belongs W1, and the zero vector is consistent to W2. Now, just you have to write the linear sum of the element is alpha 1 plus 0 bar. Now, comparing it with the W1 plus W2, because W2 element is zero vector. That's why alpha 1 equal belongs W1 plus W2. Therefore, the same element is also repeated in W1 plus W2, sum of the subspaces. That's why W1 contained are equal to W1 plus W2. And in the same manner, next one, W2, in the similar way we can prove that W2 contained are equal to W1 plus W2. Therefore, union of any two subspaces is the first contained are equal to W1 plus W2 is there. Now, this is one of the important sum is there. Okay. Next one, this problem is also very important. W1, W2 be a subspace of a vector space. Sum of the subspaces must be equal to the vector space. And intersection of the subspaces is generated 0 bar. Now, these problems are also see and refer in your textbook. There is no problem. But some problems are not included in your textbook. Okay. That's why just you have to now for your awareness, and I will provide through WhatsApp is there. I have to provide the through WhatsApp. Okay. Intersection of the subspace is zero vector. Prove that for each vector means alpha belongs to B. There are unique vector alpha 1 belongs W1, alpha 2 belongs W2. Therefore, sum of the vectors is equal to alpha. Okay, that's enough. That is the linear sum of the part. Okay. Now this is also number of times repeated in the final examination. Okay, please note down. Next one. Here alpha being the one of the vector and same vector is consisting the sum of the subspaces. So therefore, according to this condition, W1 plus W2 equal to B is there. B element is alpha equal to this element is alpha 1, this element is alpha 2. So that's why alpha equal to alpha 1 plus alpha 2 is there. Next one, if possible, let alpha equal to beta 1 plus beta 2 because beta 1 belongs to W1, beta 2 belongs to W2. Therefore, when both are equal, when alpha equals to beta and those linear sum elements are also equal here. That is alpha 1 plus alpha 2 equal to beta 1 plus beta 2. Now that is the well defined of this part here. Now this element is also consisting alpha 1 minus beta 1 from the above the test is the first test of subspace. Now this is also consisting W1 and this element is also consisting W2 because in the same manner alpha 1 minus beta 1 belongs to W1. Now this element is also equal to this one. That's why this is also belongs to W2. So alpha 1 beta 1 belongs to W1. Same element is also repeated in W1 and W2. That's why alpha 1 minus beta 1 belongs to W1 and W2. Therefore, already given the condition is this element is equal to zero vector is there. Now this is generated 0 or 0 vector, whatever it is. When it is alpha 1 minus beta 1 equal to 0 vector, alpha 1 equal to beta 1, this element is also equal to beta 2 minus alpha 2. Therefore, that is also equal to 0 vector. We are getting the result is alpha 2 equals to beta 2. Therefore, because that is the uniqueness of this part. Because when it is alpha 1 plus alpha 2 equal to beta 1 plus beta 2, finally we are getting the result is alpha 1 equal to beta 1, alpha 2 equal to beta 2. Therefore, the linear combination of this part of these conditions when it is unique. Okay, students. Now, this is one of the important concept of linear sum of theorems. Okay. Now, what is the linear combination of vectors? What is the linear combination? First of all, let V of F be any vector space. Any vector must be equal to the and some field elements are there. A1, A2, so on, AN. Those are all field elements. Alpha values are all alpha values are vectors. At least one vector is an equated to sum of the scalar multiplications. Sum of the scalar multiplications. Suppose here A1 alpha 1. First scalar multiplication is A1 alpha 1. Second scalar multiplication is A2 alpha 2. And AN alpha n. Those scalar multiplication under the addition vector addition is closed in between A1 alpha 1 plus A2 alpha 2 plus 1 AN alpha n. This is the combination of the part. Okay, that combination must be equal to any non-zero vector is there. Any vector means gamma equal to A1 alpha 1, A2 alpha 2, 1, AN alpha n. This type of system is called linear combination of the vectors alpha 1, alpha 2, 1, alpha n. Here gamma is a vector. Gamma is a vector. Now that vector belonging to vector space of the field. Okay, that is the linear combination means any vector must be equal to the sum of all the linear combination, sum of all the scalar multiplications. Okay, that is summation ai alpha I. Now you have to write the number of linear combinations given in the non-empty subset of a vector. Now that is called a linear span. Okay. Now it is simply the set of all the possible linear combinations of all possible finite subsets of S. Here suppose P of F be any vector space, because S be the non-empty subset, and the subset of the elements to write the scalar multiplications according to scalar multiplications to arrange the linear combination of this part. Now directly we have to finite subsets of the part to write the possible finite subsets and write the linear combinations of vectors. Now that is called the linear span. Linear span is denoted by L of S. Simply the roster form is gamma be any vector from is there are two hyphens and gamma equals to this is any vector must be equal to the possible linear combinations right as the summation ai alpha I. All ai values are field elements. All alpha I values are subset of the elements. Now that is the simple definition. Suppose even if the subset must be a finite set and the linear span is also a finite set. Suppose even if the set of a vector space is finite set, but the linear span is a infinite set is there. And the linear span also sometimes that is also called okay. L of S is also called linear span or generated by subset of a vector space. Generated or spanned by subset of a vector space. It is simple one. This is linear span. Spanned by subset of the vector space or generated by a vector space. Whatever L of S is simply read as. Suppose given the set is empty subset. Empty subset means what is the linear span element? That is zero vector, only generated zero. This is also one of the important things. And the subset is contained or equal to that subset is a subset of L of S linear span. Now, this is the definition of linear combination and the linear span. And some theorems are also we have to explain here. What are the theorems? Linear span is always a subspace. Yes, so it's very simple. Suppose we will prove that linear span is a subspace. What is the subspace condition? Alpha plus b beta. And we are taking the linear span elements is alpha and beta is there. And the field of the elements is A and B. What is the subspace condition? That is A alpha plus B beta is there. Alpha can also be written as summation AI alpha I equal to 1 to M is there. Beta vector can also be written as summation BI beta I. Here I equal to 1 to N is there. Okay. A alpha plus B beta means A of alpha means A1 alpha 1, A2 alpha 2, AM alpha M. Plus B of B1 beta 1, B2 beta 2, so on Bn beta N. That equals to, now this combination can be also be listed as AA1 of alpha 1, AA2 of alpha 2, so on AAN of alpha M. This is BB1 beta 1, BB2 beta 2, so on BBN of beta N. So therefore, A alpha plus B beta is a linear combination of a finite set. Those alpha values, beta values, those are subset of the elements. Now, subspace condition is A alpha plus B beta belongs to L of S. That's why A and B be any field elements, alpha and beta be any subset of the vectors and the linear span of the elements, that is L of S. Final condition is subspace is A alpha plus B beta belongs to L of S. That's why linear span is a subspace. Okay, now that is a very simple theorem of linear span. So, linear span is the intersection of all subspaces of P which contain S. That is a simple theorem. Because A contained are equal to B, B contained are equal to A. That's why A equal to B is there. And in the same manner, W is a subset of P of F containing S, and every linear combination of finite set of elements, that is W is also closed. Because every linear combination of finite set of elements of S is a linear span. That's why L of S contained are equal to W. Because L of S contained are equal to intersection of all subspaces of P containing S is there. Therefore, finally, S contained are equal to L of S. Therefore, finally, what is the final statement? L of S means linear span means it is the intersection of all subspaces of P which containing S. That's enough, students. Now there are some problems on linear spaces. Just you have to observe here any one of the vector is alpha. Alpha equal to 1 minus 2, 5 is there. That vector to write as a linear combination of the vectors E1, E2, E3. Okay, this vector to write as the linear combination of the vectors according to these three vectors. What is the linear combination of the vector? Now here gamma equal to or del equal to, this is x E1 plus y E2 plus z E3. This is the linear combination of the part. You find the values of x, y and z. So already we know that alpha equal to 1 minus 2, 5. What is the linear combination definition? Linear combination is any vector must be equal to the sum of the scalar multiplication. That is x into, we are given the vectors 1, 1, 1 plus y into 1, 2, 3 plus z into 2 minus 1, 1 is there. Now to arrange the first coordinates of the elements. This is x plus y plus 2z first coordinate. This is x plus 2y minus z. This is the second coordinate. Third coordinate is x plus 3y plus z is there. So both are equating on both sides. We are x plus y plus 2z equal to 1, x plus 2y minus z equal to minus 2, x plus 3y plus z equal to 5 is there. Now, these three equations to arrange the matrices representation. First of all, to write the coefficient matrix 1, 1, 1, 2, and augmented part is 1. Constant element is also included, that is the augment matrix. Like 1, 2, minus 1, and the element is minus 2. 1, 3, 1, and 5. Now, first of all, R2 minus R1. 1 minus 1 is 0. 2 minus 1 is 1. Minus 1 minus 2 is minus 3. That's it. Now, this is this element is minus 2 minus 1 is minus 3. Another one is also there. In the same manner, this is also applying here R3 minus R2. Now, this is the row operation and the column operation. When it is equating to 0, echelon form means maximum row is 0 is there. Okay, maximum row of the maximum third row and either maximum of the second row is also 0. Either upper triangular or lower triangular of the form. That is, this is the lower triangular, this is the upper triangular of this part. 1 minus 1 is 0, R2, R3 minus R2. Okay, next R3 minus R2 again, also apply. We are getting the matrices there. Finally, we are getting to write the alpha plus beta plus 2 gamma equal to 1 and 0 alpha plus 1 into beta minus 3 gamma equal to, and it is the another element is minus 3. and finally 5 gamma equal to 10 is there, because augment elements, constant elements is also repeated here. Okay, therefore when these three equations are solving, 5 gamma equal to 10, gamma equal to 2 is there. That gamma value substituting here, we are getting the beta value. Beta and gamma value is also substituted in the first equation. We are getting the element is alpha. Now those alpha beta values, those values substituted in the combinational part. Now that is x value, y value, x value is there. Minus 6 E1 plus 3 E2. Now the nothing but is there. Here alpha x equal to alpha, y equal to beta, z equal to gamma is there, because that is also conversation of this part. Okay. Finally, alpha equal to minus C1 plus 3E2 plus 2E3. That is the first problem of linear combination of this part. Second one is any vector cannot be expressed as a linear combination. Cannot be expressed as the linear combination of three-dimensional part. Now E1, E2, E3 is given. Alpha equal to AE1 plus BE2 plus ZE3. That is a linear combination. Alpha is given, the vector must be equal to combinatorial parties AE1, BE2, CE3. A of E1 given, E2 is given, E3 is given. Okay, that is all the first coordinates of the elements must be added here. A plus 2B plus C equal to 2. And the second coordinate of the elements, second equation, third coordinates of the elements are, that is third equation. Now, these three equations to arrange the coefficient matrix and augmented matrix of this part. Okay. Now, just you have to see and refer this matrix. 1, 2, 1, and 2 is there. Minus 3, minus 4, minus 5, and minus 5 is there. 2, minus 1, 7, and 3 is there. Okay. Now, this matrix R2 plus 3R1, we are getting the element is 0. R3 minus 2R1, this element is also 0. Okay. Now these and the remaining the equations, just you have to observe it here. After the simplification and get a after the C and the matrix, here third equation of the variable part is 0. So that's why even the system is inconsistent. Inconsistent means the equations have no solution. That's why alpha cannot be expressed as a linear combination of the. That's enough, students. And this example are also very important in the final examination, either a short answer or fill in the blanks. Even in the subset, just you have to see and refer. Now, this number of times this question, this problem or this important part given in the APR set and the PG sets are there are so many universities the PG set is there. Now, given the subset of the elements 1 0 0 0 1 0 0 0 1 of P3 of R. So x coordinate 1, y coordinate 1 in the second point, third coordinate 1 in the third point. These 3 points given the subset is there. Now this is the 3-dimensional of the part P3 of R. We have P3 of R generates the entire vector. Entire vector is not consisting of P3 of R. Therefore, ABC belongs to B. Then we can write ABC equal to A of 1 0 0 plus B of 0 1 0 plus C of 0 0 1. Okay. Now here A, B, C also belongs to L of S. ABC is also consisting of the vector space is there. Therefore, that's why B contained are equal to L of S. Or L of S contained are equal to B. Finally, A contained are equal to B, B contained are equal to A equals to B is there. That's why L of S equal to B. Okay. Now here the regular basis in R cube of R cube of R or R V3 of R, whatever it is. 3 coordinates of the point, that is 1 0 0 0 1 0 0 0 1. There are 3 standard bases. Standard basis, OR, usual basis, OR, regular basis. Please note down the students. What are the standard basis of V3 of F? 1 0 0 0 1 0 0 0 1. Okay. What are the standard basis of V2 of F? 1 0 0 1. 1 0 is the one of the point. 0 1 is the one of the point. Given the set is the part is V2 of F or R square of R. That is the 2-dimensional of regular spaces. 3-dimensional of regular spaces is 1 0 0 0 1 0 0 0 1. 4-dimensional of vector space. V4 of F, usual basis or regular basis or standard basis. 1, 0, 0, 0, 1 point. 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, that's it. Now here, that is the V4 of F. In the same manner, n-dimensional of vector space is 1, 0, 0, so on 0. That is the usual basis. 0, 1, 0, so on 0. 0, 0, 1, so on 0. 0, 0, 0, 1, so on 0. These are all so on. 0, 0, so on 1 is there. These are all n-dimensional of vector space of the usual basis. Even E2, E3, so on here. Now, usual basis are regular basis or standard basis notated as even E2, E3, so on here. Suppose in 3-dimensional of the path V3 of F is given. Now it is generates the entire vector space V3 of R. That's why you are getting the result is L of S equal to E is there. Okay. Now that's enough. Tomorrow already time is over. Okay. And one of the problem is also explained here. Okay. The vector space R cube of R, alpha, beta, gamma. There are 3 vectors given in the set is there. Now these 3 vectors surrounding the subsets S and T. According to the subsets and through the vectors must be generated. Now here given in the subset is generated in alpha beta vectors. T is also one of the subset generated in the alpha beta gamma. That's why linear span L of S equal to L of T. Given in the subset of the vector space is alpha and beta, that must be spanned, that is L of S. And alpha beta gamma given in the set of the region given in the subset is T, that is also spanned, that is L of T. So finally we must prove that we will prove that L of S equal to L of T. Both are same. But this is one of the very most important problem in the final examination. Suppose first of all, so you have to write the linear span of T, L of T. What is the L of T? Linear combination of vectors of T. So given the T subset is T set of the form is alpha beta gamma, and according to those vectors you write the linear combination A alpha plus B beta plus C gamma. That is such that here A, B, C being the real numbers. That is the linear span of the set first form. Suppose gamma equal to third vector gamma equals to another 2 vectors to write as the linear combination X alpha plus Y beta. Right, the gamma value is there 3 minus 4 5 equal to X of alpha value is 1 to 1 and the beta value is 3 1 5. And to arrange the elements X plus 3y and 2x plus y and X plus 3y. Now those elements are equivalent to gamma vector 3 minus 4 5. Now we are getting the 3 equations. These 3 equations we must find out the solution. We are getting the value is X value minus 3, Y value 2, Y equal to 2. These 2 values are satisfying all the 3 equations. So finally, replacing the values in the linear combination of this part, 3 minus 4 5 equal to minus 3 of 1 to 1 plus 2 of another vector is 3 1 5. Okay. Finally, you multiplying with the C is there. C is multiplying given in this one. C into 3 minus 4 5 equal to minus 3C of 1 to 1 plus 2C of 3 1 5. So this value is C gamma equal to another one minus 3C and this is alpha and this is beta minus 3C alpha plus 2C beta. Now what is the linear combination A alpha plus 2 beta plus C gamma? 3 beta plus C gamma. C gamma value substituting in the linear combination. So that is A minus 3C of alpha plus B plus 2C of beta. So we are getting the values of in the linear combination alpha beta gamma, and finally we are getting in the terms of alpha and beta. So this is also linear combination. Alpha and beta means spanned by the element is S, spanned by S. Alpha beta gamma means spanned by T. Therefore finally B alpha plus B beta belongs L of S. Therefore L of T equal to L of S. There. That's enough. This is one of the important problem. Last one. In this section, last one is in the vector space R cube of R. R cube of R vector space and S equal to 1 0 0 0 1 0. X coordinate 1 and Y coordinate 1. Find L of S. That is the LFS. Now, of simplification, 100 and 010, A alpha plus B beta. We are getting the values A 00 plus 0B0, adding with the AB0 is there. Z coordinate is 0. That's why in the geometrical expression Z equal to 0. That is the plane of LFS. Okay. And according to the set of vector space of the subset is 100, we are getting the plane is Z equal to 0. That is the linear span. Suppose 010, is given and linear span in the plane x equal to 0 is there. 100, is the given in the set. Find LFS and linear span is the plane y equal to 0 is there. According to the linear span definition, alpha being the vector, the vector is consisting according to the subset of the elements. We have 100 plus, we have 010. We are getting the element is AB0, Z coordinate is 0. That's why we are the plane is Z equal to 0. Suppose another x 010 is there and x equal to 0 is the plane we are getting. And in the same manner 100, is there and the linear span in the plane y equal to 0 is there. Now there is one of the important part is there. Okay. Now it's very important the fill in the blanks, either fill in the blanks or the match the following or multiple choice. Okay. That's enough. Thank you, students. Now this is one of the important session. Please note down all the materials must be submitted in the WhatsApp. Please refer and one more time is there. Number of times I explained here. Okay, all the material posted and especially these sessions materials are also submitted in the WhatsApp group. Okay, see and enjoy and to practice more number of times is the number of times in your as an your own effort. Okay, thank you one and all students. Wish you all the best and wish you good luck. Hello. 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 Anybody is there? Respond here. Hello.
Yes, sir.
Okay, once again, wish you all the best. Thank you one and all. Tomorrow we will meet same time, same class. Okay.
Thank you, sir.